Welcome to the fifth lecture on graph theory. So, today we will learn a special type of graphs called trees. A tree is a connected acyclic graph, and a collection of trees is called a forest. So, we learn few results related to trees, and then we move to minimum spanning tree. Given weighted graph, how to find minimum spanning tree of the given graph using Kruskal algorithm. So, let me formally define what is a tree. So, a tree is a connected acyclic graph and a forest is a graph in which each component is a tree. Okay. So, acyclic means the graph has no cycles. So, let me give some example of trees now. So, this is a tree. This is a tree with one vertex. This is a tree because this is connected graph and there is no cycle here. This is tree with two vertices. So, this is a tree because it is a connected graph and there is also no cycle. So, it is a acyclic connected graph, and this is tree with three vertices. So, this is a tree with four vertices, and this is another tree with four vertices. So, the other trees with four vertices. Okay. And so, this is one tree with 5 vertices, and this is another tree with 5 vertices. They are not isomorphic. So, these two trees are not isomorphic, and so this is these are all trees with 5 vertices. Okay. And every tree and okay, let me first define what is a leaf. A leaf of a tree is a vertex of degree 1. So, so these are the leaf nodes. This is a leaf, this is a leaf, this is a leaf node. These are leaf nodes. Okay. So vertex of degree 1 in tree is called a leaf. Now, we will prove a theorem related to tree. Every tree with n vertices, n greater than equal to 2, has at least 2 leaves. Okay, so that sort of you can observe that this is correct, that every tree with at least 2 vertices has at least 2 leaf nodes. So this is a tree with 4 vertices, it has 2 leaf nodes. This is a tree with 2 vertices and both are leaf node. This is a tree with 3 vertices, so it has 2 leaves. So here both are leaf node because both are of degree 1. So this graph or this tree has 2 leaf node, this tree has 3 leaf node, and this tree has 4 leaves. Okay, so this is quite clear, but we need to formally prove this one. Proof. Suppose tree T has n nodes, vertices. And let P be the longest path in T, and the longest path is this one, V naught, V 1 up to V k be the longest path in T. Now, since P is longest, every neighbor of say V naught lies on P. Why this is true? Let me so this is the longest path. So now suppose V naught has you know what is neighbor, right? First of all, you know what is neighbor. So the neighbor of this vertex, so the neighbor of this vertex are this node and this node are the neighbor of this vertex. So what it says is that all the neighbors of V naught are on this path. If there is another neighbor of V naught which is not in the path, say something V star, which is a neighbor of V naught, but it is not in this path, then you can get a longer path than this path, because you can sort of add V star here to get a longer path than this one. And since we have assumed that this is the longest path, so that is why all the neighbors of V naught lies on P. Okay. And since T is acyclic graph, V 1 is the only neighbor of V naught, because this is a acyclic graph. So, of course, these two are there in the path, means these two are adjacent, and then V naught can't have this also as a neighbor, then this will form a cycle, but the graph T is a acyclic graph. So, V 1 is the only neighbor of V naught. So, that is why the degree of V naught is equal to 1, because it has only one neighbor, that is V 1, and using the similar argument we can also prove that V k is also of degree, V k has degree 1. So, similarly degree of V k is equal to 1. So, what we have proved is that a tree with at least 2 vertices has at least 2 leaves. Okay. And next we prove another result related to tree. Okay. So, this is another theorem. Every tree with n vertices has exactly n minus 1 edges, because of the property of the graph that the graph is acyclic and connected. Because of that, every tree with n nodes has n minus 1 edges. Let me just illustrate this thing using the example that we have in the previous page. So, here you can see that, so this is a tree with 5 vertices. So, n equal to 5 here, and the number of edges is E denotes the number of edges. So, the number of edges is 4. So, it has n minus 1 edges. So, whichever tree you take, this is true. This is a tree with 4 vertices. So, n is equal to 4. So, the number of edges is equal to n minus 1. I can see that there are 3 edges. Okay, but we need to prove this result that every tree with n vertices has n minus 1 edges. So, we will prove this formally, and we will prove this by induction. We have proved some theorem using contradiction and different cases. This is perhaps the first time we are proving a result in this course by induction. So, induction goes in this way, whether this result is true for n equal to 1. So, n equal to 1 means a tree with only one vertex, and this is the tree with one vertex. So, n equal to 1 here, and the number of edges is equal to n minus 1, 0, it has no edge. So, this theorem is true for n equal to 1, and then this is the induction hypothesis. Suppose every tree with k vertices has k minus 1 edges for k greater than equal to 1. So, this is the induction hypothesis, that every tree with k vertices has k minus 1 edges, and let T be a tree with k plus 1 vertices. And then we have to prove that the T has k edges. Now, since k plus 1 is greater than equal to 2, this T has at least 2 leaves. So, here I am just so T has a leaf node for sure, T has a leaf say x. Now, I will denote this thing that the graph T minus x, that means from the tree I am removing this leaf node x. So, how this operation goes? Suppose I have this tree for example, and this is a tree with 5 nodes, and this is a leaf node, this is a leaf node, this is a leaf node. So, there are 3 leaf nodes, and suppose this node I denote by x, and this is my current tree T. Now, what I mean by T minus x is that you remove this node from this graph. So, when you are removing a node, you have to remove the adjacent edge also. So, after removing this vertex x, and the T minus x is this tree. This is what the T minus x is when T is this one and x is this node. Okay. So, the graph T minus x then is a tree with k vertices and by induction hypothesis this is my induction hypothesis. I have assumed that every tree with k vertices has k minus 1 edges. So, by induction hypothesis T minus x has exactly k minus 1 edges, because T minus x is a graph is a tree with k vertices. So, by induction hypothesis T minus x has exactly k minus 1 edges. Now, since T has one more edge than T minus x, here you can see that this is your T minus x and this is your T. So, T has one more edge than T minus x. since t has one more edge than t minus x, the tree t has k edges. So, this is how you prove using induction hypothesis that you first prove to prove a theorem using induction hypothesis. First you prove that the base case is true, that means you prove that statement is true for n equal to 1, and then you assume that the statement is true for k, that means here the statement is true for tree with k vertices, that every tree with k vertices has k minus 1 edges, and then finally you have to, assuming that this is true, you have to prove that a tree with k plus 1 edges, a tree with k plus 1 vertices has k edges, and that is complete the whole proof. We will talk about another theorem. In a forest, with v vertices and k components, the number of edges is v minus k. Okay. So, you understood what is forest, right. So, so this is, so forest consists of several trees, each component is a tree. So, let me just draw a forest. So, this is an example of a forest, because this is one graph, the whole thing is one graph, and this is a forest, and it has 3 components. And let me call this one, the first component is T 1, second component is T 2, and the third component is T 3. In general, I am assuming that this tree has V 1 vertices, this tree has V 2 vertices, and say suppose there are k components in general, and this tree has say V k vertices. If tree T 1 has V 1 vertices, then it has V minus 1, V 1 minus 1 edges. So, this is the number of edges, this is the number of vertices, and second tree has V 2 minus 1 edges, and the kth tree has V k minus 1 edges. So, the total number of edges in the tree in the forest is equal to summation of V I minus 1, I is from 1 to k, which is equal to summation of V I equal to 1 to k minus k, and summation of V I from 1 to k is equal to the total number of vertices. So, this is V minus k. So, we have proved that, of course, this is I am using the previous theorem to claim that okay, a tree with V 1 vertices is having V 1 minus 1 edges, and from this theorem follows from the previous theorem. So, we have proved that the number of edges in this forest is V minus k. So, next we just state another theorem related to tree. The following statements are equivalent. The first statement is T is a tree. So, I will not prove this theorem just for your information. These are easy, you can refer some book for the formal proof. T is a tree, which is equivalent to say that T is connected graph and has exactly b minus 1 edges. So, T means it is T, B is the vertex set and E is the edge set. So, A is equivalent to B, and the third statement is T is connected, T is acyclic and has exactly p minus 1 edges, and D is the another statement. Any two vertices of T are joined by a unique path. This is very much helpful because there is no cycle. As you can see, let me just draw a tree quickly. So, this is a tree, and now you consider any two vertices, say this vertex and this vertex. There is a unique path between these two vertices. So, the path here clearly you go from here to here, and this is the unique path between these two vertices. Okay? And since tree is a connected and acyclic graph, any two distinct vertices are joined by a unique path. So, so we have learned what is a tree, what is a forest, and some basic results related to trees and forest. So, in the second part of this lecture, we learn what is a minimum spanning tree in a weighted graph. Thank you very much.